value. So it's useful to know the general result from the perspective of the phasor diagram as well to derive that earlier result that I just derived for you for the n oscillator or n source case, but now using phasors. So here we can see we have, say, again, I've just drawn it for the case of 6 phasors at some arbitrary angle phi. Sorry, I chose phi in this diagram here rather than delta, but let's just assume now that the angle between the adjacent phasor or the phase difference between them is phi. Then A1, A2, A3, each one is rotated by an angle phi with respect to the previous one. And the resultant phasor, AR, is the phasor from point O to the tip of this point, which I call T. So we need this value OT, and we first established that all of these are clearly on a circle, right? They're going to be on the tip of a circle. All of these phasors are going to follow a circular pattern, and we can establish exactly what that circle's radius is. Let's say the radius of that circle, this is Q, and this distance is R, and so is this distance R. Because this angle phi is the same as this angle phi, because the radius R is always normal to the tangent to the circle, and therefore R's are all, these two are exactly perpendicular to these two phasors, and therefore they have the same angle phi. So right away, because this, in this triangle over here, we can see that A1 divided by 2 is R sine phi over 2. So the amplitude of A1, which is OS, simply 2R times sine phi over 2. And similarly, the central angle or the opening angle of this polygon over here, which is not complete, obviously it's not a complete polygon, but is now n times phi, where n is the number of phasors. And we see that again, we can calculate this resultant field amplitude AR by just looking at this triangle over here. Sorry. So in this triangle now, because the total angle is n phi, each of these individual angles, which are the bisectors, which are bisected by this right angle, that angle is n phi over 2. Again, I can use that triangle to obtain AR is 2R times n sine n phi over 2. And therefore, just by dividing one by the other, eliminating the radius R, I obtain AR divided by A is sine n phi over 2 divided by sine phi over 2. So this is a very nice pictorial or geometrical way to derive the same result that we did with the geometric series. So now I want to, and I'll come back to this later when we do the n-slit case, to talk a little bit more about various secondary maxima and so on. But first, let me now take the limit as n gets larger and the spacing d gets smaller, because then we get what we call a line source. And now we can define an effective source strength per unit length, which is over here. This is just simply in the limit n going to infinity of the source strength of each individual oscillator times n divided by d. And I call that EL. And because I have a now a spherical wave that's emanating from each of these points, these emitters, I want to take into account that that spherical wave amplitude actually falls off with the distance. So I'm going to now treat the situation where I have this line source that's extending along the y direction, and I have the z plane, and I'm looking in the sort of the xy plane. This angle theta relative to the central propagation direction is this angle theta. I'm looking at this point P over here, and I want to examine what the phase will be at this point P. So I redraw that over here. Here's that central line source. The distance from the center of the source is to any point in the line is characterized by the distance y. And Here is x, the direction along away from the line source, normal to the line source. And again, we look at any point P over here. That distance is r from the emitter over here. The distance from the center is capital R. The amplitude, of course, for a source y will go as EL divided by small r, but I'm going to assume here that small r is almost equal to r in the amplitude, but we cannot neglect the fact that r is not exactly capital R in the phase, because as you know, when the phase changes even by a little bit, it can drastically affect the output of the sine function. So we need to be careful about the phase. So applying the cosine law to this triangle over here, this hopefully it's clear which triangle, but I'll just outline it. Sorry, I didn't do that very good, but this angle is pi over 2 minus theta. So in this triangle over here, I can apply the cosine law. R squared equals y squared plus r squared minus 2yr sine theta. And I can take the square root and expand in a binomial series. It's not too difficult to get this result, r minus y sine theta plus y squared over 2r cosine squared theta. And so we see now that the distance, or the phase value in here, small r, from this point y is dependent on capital R, which is effectively a constant. It just basically defines how far away we are from the center of the slit, or the center of the line source in this case. This small r is dependent on y, the aperture variable, or the line source variable in this case, linearly. And so this is a Fraunhofer condition. We can neglect any terms that go higher than y. And then we obtain the result that the electric field is simply the integral now, rather than just the, in the earlier case, we had finite number of line sources, a finite number of point sources. Now we have an infinite number, so we need to integrate over y. Okay, we can carry out this integration. It's just linear in the y variable. So we just expand that function as using the trig identity. And this factor, the second factor here, will vanish. I want you to think about why, and I'm sure you'll figure it out. And so if you integrate this first factor, the first part, and simplify it, you get this result. Okay, and it's just straightforward integration. Change the variables from ky sine theta to some other variable, and then integrate it, and you'll get this result. And as you can see here, this term over here is just simply sine omega t minus kr. This would, and divided by capital R, this is just the amplitude, and this is the total wave that is propagating from the center of the line source to the point, to the observation plane where P is located. But this term over here, this sine kd over 2 sine theta by kd over 2 sine theta, this is reminiscent a little bit of other function that we just saw, but it is slightly different than that other function. So if I rewrite it, I'll call this function sine beta over beta, where beta equals kd over 2 sine theta. And as I already said, this part over here is just a spherical wave from the center of the line source. Okay. And the irradiance is just obtained by squaring and setting this sine squared average of sine squared omega t minus kr must be just set to half, and we get that I of theta is I of 0 sine beta over beta the whole square. This function sine beta over beta is called the sinc function, and this is therefore the irradiance is a sinc squared function. So I've plotted here the sinc function sine u over u. You can see that it has a maxima at the center and undergoes a minimum over here, and you can immediately see what value of beta must give you the minimum, because sine beta needs to vanish. Sine beta will vanish first at beta equal to pi. So the intensity of a line source in this Fraunhofer approximation, remember that the angle theta which features in beta. Remember, beta is dependent on, of course, d, the size of the aperture, size of the line source, but also the angle theta in the xy plane. That is what is making this u the variable, or beta the variable, vary. So we can look at one simple limit. When d is far greater than lambda, then beta, if you remember from here, if d is far greater than lambda, beta is going to be very large, so the intensity drops off rapidly with angle. So even small changes in angle cause this intensity to vary rapidly. So the long line source that we had, because the intensity is just going to be mostly confined to the central region, so the line source just looks like a point emitter, right? Because it's just got some intensity right at the center when theta equal to 0, and then vanishes away from the from that. And so it's basically like a point emitter at the center, emitting primarily circular waves in the xz plane. So going back to this picture over here, in this, what I've said is that if this entire, if d is much greater than lambda, if this length along this direction is much greater than lambda, then most of the intensity is confined to a small band right at the center, right here. This is, remember, this is in the xy direction. This theta angle is in the xy direction. And in the z direction, of course, we can have some other waves. So if I replace all of this by a single point emitter at the center, then the output over here is just the single point emitter, and it's a spherical wave, or sorry, a circular wave that is propagating in the xz plane that's going to come out, which is just governed now by this angle, by this p, the position p in the xz plane over here, because of that r factor. Okay, so that was an important result. So the long line source looks just like a point emitter at the center, emitting primarily circular waves in the xz plane. So I will pause now and stop this video, and I'll ask you to go and answer